we're going to look at mole ratios within a chemical formula or a chemical reaction, and we're going to be able to use it as a conversion factor. Okay. So when I say conversion factor, that means that allows us to convert from one substance to another. Okay. Stoichiometry and chapter 9, which is where we're at right now, is going to be like the chapter of T-charts. Okay, so you need to get really comfortable with the T-chart process, which is why we practiced it a little bit last class as well. Okay. Okay, so we're going to use this mole ratio step to determine the conversion factor between two substances in our chemical reaction. Okay, so if I look at this balanced chemical reaction here, and you're welcome to write it down. You don't have to if you just want to watch what we're doing here. First of all, when we look at any chemical reaction, the first thing we have to determine is our reaction balanced, yes or no? So I want you to just kind of quickly glance over this one, see if you can determine if it's balanced or not. Okay, yes, do we think it's balanced? Right, we have 2 potassiums on the left, 2 potassiums on the right, 2 chlorines on the left, 2 on the right, and 6 oxygens on either side. Okay, so we have a balanced chemical reaction here. Can anyone tell me what type of reaction it is? Decomposition. Good. We go from a complex molecule to 2 simpler molecules. Okay, we've broken down our potassium chlorate molecule. Good. Okay, so now the mole ratio between potassium chlorate and oxygen gas, can anyone tell me what that mole ratio is? 2 to 3, right? That's it. 2 to 3. All we look at when we look at mole ratios is we look at the coefficient in front of that molecule. So the mole ratio between potassium chlorate and oxygen gas is 2 to 3, which means it takes 2 moles of potassium chlorate to break down and form 3 moles of oxygen gas. Right? That's what that mole ratio is telling us. It's a quantity. So not only if we look at it on the molecular level does it take 2 potassium chlorate atoms, or molecules, to break down into 3 oxygen gas molecules, it takes it on the mole ratio or the mole scale as well. Mm-hmm.
So why do you look at the one, the thing before it?
Why do we look at the coefficient?
Like this 2KCl.
Oh, this one just wasn't involved. We just didn't bother with this one.
Oh.
If we wanted to find the mole ratio between potassium chlorate and potassium chloride, we would say it's 2 to 2, right? So it just depends on what 2 compounds we're looking at. So in our stoichiometry problems, we'll always only be comparing 2 substances in our compound. We won't do any more than 2. Okay? Okay, so in this reaction, it takes 2 moles of potassium chlorate to make 3 moles of oxygen. Okay, why don't you go ahead and balance this chemical formula now listed below here. Okay, can everyone see that okay? Go ahead and try to balance that real quick, and then we'll look at some mole ratios. So we want to balance the formula first, balance the chemical reaction first, and then we're going to look to find the mole ratio between copper and silver. Okay, is that what we had balancing? 1, 2, 1, 2? Mm-hmm. Okay, you can leave the 1s off. So that means the mole ratio between copper and silver is what? 1 to 2, right? It takes 1 mole of copper combined with silver nitrate to form 1 mole of copper nitrate and 2 moles of silver. Okay, so that's what we need to be thinking about when we balance these reactions is how much of it does it take. So a question for stoichiometry might say, if we start out with 30 grams of copper, how many grams of silver could we yield, right? And so in order to get there, we're going to build a T-chart, but we have to include that mole ratio step, which tells us 1 mole of copper is needed to form 2 moles of silver. Okay, so we're going to need that part of it, but that's what the question might look like, right? Or it could ask, if we start with 3 moles of copper, how many grams of silver, right? There's a lot of different ways we can go with that. But basically, we're going to put quantities now to our reaction. Okay, so we're going to start with the simplest types of conversions, which is moles of one substance to moles of another. Okay, it's a really short T-chart, and then we're going to kind of build from there. So the first thing we're going to do is we're going to look at taking the amount of our substance in moles, and we're going to solve for the amount of our unknown in moles. Okay, and these are the easiest types of problems that we have. So this is a mole to mole conversion. Okay, so we're going to look at the quantities of our unknowns in mole values. So we don't have to deal with molar mass, anything, right? Our conversions are extremely simple. Okay, so let's go ahead and look at this equation, and we'll go ahead and get it balanced real quick. I think we feel pretty comfortable with balancing equations, so I don't want to spend too much time on that. But just go ahead and try and balance it real quickly, and I'll have it balanced up here too. Yeah, lithium. Okay, so we're going to look at how many moles of lithium hydroxide are required to react with 20 moles of carbon dioxide. Okay? How many moles of lithium hydroxide are required to react with 20 moles of carbon dioxide? So if I put in 20 moles, how many moles of lithium hydroxide do I need to get out our final products? Okay, so what we're going to do is we're going to start with what we know, always in our T-chart. Start with what we know, 20 moles of CO2. And I want to go to moles of lithium hydroxide. So sometimes I'll put it up above my chemical reaction so I kind of know what's the mole ratio I need to look at, right? I'm starting with 20 moles here, and I want to find out how many moles of lithium hydroxide. Okay, so in my T-chart, this is the simplest type we'll do, but we need to go from moles of carbon dioxide to moles of lithium hydroxide. Okay, so we're always going to cancel directly right here, and we want to go to moles of lithium hydroxide. So this right here is called the mole ratio step. Okay, this is the only part in our T-chart that we could ever have two different substances in the same column. Right? Lithium hydroxide and carbon dioxide are two different substances. The only time that we can have two substances is when it is mole to mole. Understood? Okay, some of you will still do that incorrectly. The only time we can have two different substances in the same column of our T-chart is when it's mole to mole. Okay? So in our past T-charts, we've said that the mole always gets the 1. Right? That's not the case in the mole ratio step. The numbers that go right here in our mole ratio step have to come from our balanced chemical formula. Okay? So since we had our coefficients as 1, 2, 1, 1, the coefficient that goes with carbon dioxide is 1, and the coefficient that goes with lithium hydroxide is 2. Right? That's where our mole ratio comes in. We said it takes 1 mole of carbon dioxide plus 2 moles of lithium hydroxide to yield a mole each of lithium carbonate and water, right? So that's where our mole ratio step comes in. That's all we're doing, right? We've canceled moles of carbon dioxide, we multiply across the whole top, which tells us we needed 40 moles of lithium hydroxide. Okay? Does that make sense? Is our answer reasonable here, right? The ratio to begin with was we needed twice as many moles of lithium hydroxide. And if we started with 20 moles of carbon dioxide, it should make sense to us that we need 40 moles of lithium hydroxide. Yes or no? Yeah. Feeling good about that? Okay, so in our mole ratio, in our mole to mole conversions, our T-chart is extremely simple, right? It's 1 mole to the other. That's it. Okay? All right, let's try. Oh my, I did too much work here. Okay. I'll balance this one for you. Maybe. Ooh, let me use a different color. So 4 oxygens on the left, 4 oxygens on the right, 4 hydrogens on the left, 4 hydrogens on the right. Okay, so how many moles of O2 will result from the decomposition of 5 moles of hydrogen peroxide? So here we start with 5 moles, and we want to know how many moles of O2. So start with what we know. Okay, so what value will go here? Right, what values need to go in those spots?
1 is the top.
The coefficients, right? So on the top would be a 1, and with hydrogen peroxide should be a 2. Okay, so these numbers are always the coefficients from our equations. Okay, always, always, always the coefficients. Which means we should end up with 2.5 moles of O2.
So can we just do those ones in our head?
Yes. Yeah. If you feel comfortable doing that, yes. Okay, we know we started out, we need, right, our mole ratio is 2 to 1, so we need double the amount of hydrogen peroxide as oxygen gas. So if we start out with 5, we're going to end up with 2.5, right? Those you can do in your head if you feel comfortable with that. Okay. Any questions on mole to mole conversions? Okay. All right, now we're going to take it a step further, and we're going to go from moles of one to grams of another, or grams of one to moles of another. Okay, we're going to take it a step further in our T-chart. Okay, so we're going to go from our substance in moles to grams, or grams to moles. So we add one section to our T-chart. Okay, so what mass in grams of glucose is produced when 3 moles of water reacts with carbon dioxide? So first we're going to balance our equation. I'll give you time to get the equation written down, and then I'll balance it for you since I think we feel pretty good about balancing. Okay, if anyone balanced it, is that what we should have had? Are you just trusting me? Okay. 6 carbons on the left, 6 carbons on the right. Hydrogens is 12 and 12. So oxygens is 12 plus 6, which is 18. And 6 plus 12, which is 18. Okay? So it should be good there, hopefully. Okay? So it says what mass in grams of glucose, we want to find out the number of grams, is produced when 3 moles of water reacts with carbon dioxide. Okay? So now it's not quite as simple as just doing the math in our head, because now we want to talk about grams. And grams has to do with a molar mass, so it takes it a little bit further. So we're always going to start with what we know. 3 moles of water. Okay, and we want to go from moles of water to what? Moles of carbon to what's our final step? Right, we want to know grams of glucose, but we can't go directly from moles to grams, right? We have to go moles of water to moles of glucose to grams of glucose. So here will be our mole ratio step. Moles of water to moles of C6H12O6. Okay, so this is our mole ratio step right here. So that means what value needs to go with glucose? 1. And what value needs to go with water? 6. Okay. So now I'm done with moles of water, and I'm left right now with moles of glucose, which is not what I want. I want grams. So I need to go moles down here, right? They need to go opposite if we want to cancel them. And here would go grams. Okay, so when the conversion is between moles and grams, what does moles get?
1.
Right, if moles and grams are in the same part of our T-chart, moles gets the 1, and then this needs to be our molar mass. Okay, so we need to calculate the molar mass of glucose. Do we get about 180? Okay. So we multiply across the whole top, divide by the whole bottom. Two 2.2, sorry, thank you. 2.2 moles of NH3. Okay, so we need to go from moles of ammonia to what? To what of H2O? Moles of H2O. Okay. Then we'll go from moles of water to grams of water. Okay, so here needs to be our mole ratio step. What's our mole ratio between water and ammonia? 6 to 4. Okay. Now moles here gets the 1, and molar mass of water is 18. No, 59.4. All right. Okay, feeling okay about that? Okay, I want to use the same balance formula now, and I'm going to give you a different question. Okay, I want to say how many moles of NO are formed from 39.2 grams of O2. Okay, so we're still going grams to moles, right? We still have 3 steps to our T-chart, but this time we're starting with grams of oxygen, and we want to work to moles of nitrogen monoxide. So let's see if we can figure out how to do that. Oops, it's not 6, it's 5. Okay. Okay, how many grams of NO are produced if 12 grams of oxygen is combined with excess ammonia? I'm going to get rid of this because we'll just start with what we know. Okay, so again, in your balanced equation, if you can, I like to say, right, we're looking for the number of grams, and we start with 12 grams of oxygen, right? It kind of helps you point out what mole ratios are you looking at, right? What compounds are we looking for? So we're looking for the number of grams. We start out with 12 grams of oxygen. Okay, so to get there, we need to go from grams of oxygen to moles of oxygen, then to what? Moles of NO to grams of NO. Okay? So we can't compare grams of one to grams of the other without going to moles because they don't have the same molar mass, right? They don't have the same molar mass, which means 1 mole of one substance does not weigh the same as 1 mole of the other, okay? So we're going to start with what we know, 12 grams of O2. So here's when our T-chart gets the longest, right? It'll have 4 sections. So we want to go from grams of O2 to moles of O2. Okay, do you prefer to put the numbers in now, or do all of the units then go back and put the numbers in? Numbers in now? Okay. So when we're between grams and moles, moles gets the 1, right? And what's the molar mass of O2? 32, okay? Be careful, do not put our coefficient in this spot, right? We want to tell that 1 mole of oxygen weighs 32 grams, right? 3 moles of oxygen or 5 moles of oxygen does not weigh 32 grams. Okay, so you got to be really careful there. There has to be the 1. So I'm done with grams of O2. Now I want to go from moles of O2 to what? Moles of NO. So this is our mole ratio step. Here's where we pull our coefficients in. So moles of O2 should get what value? 5, and then moles of NO is 4. Okay, so I'm done with that. Now I go moles of NO to grams of NO. Okay, here again moles gets the 1. Our molar mass of nitrogen monoxide is what, 30? 14 plus 16 should be 30. Okay. So now I've done all of my cross multiplying, and I'm left with grams of nitrogen monoxide, which is what I should have. Now I do my math, multiply across the whole top, divide by the whole bottom. Okay, with these type of problems, it's much more difficult for us to determine if our answer is reasonable or not, okay? Because we have the mole ratio, because we have different molar masses, it's a little bit more difficult for us to determine, does that number make sense, yes or no, right? We should hopefully be looking at similar ranges of numbers, right? If we start with 12 grams of oxygen, we really won't be getting thousands of grams of another product. But it's still a little bit more difficult to read there. So just make sure that everything's plugged in correctly and trust what your conversion tells you. Okay, any questions here, gram to gram? Sometimes we get up to this biggest T-chart and then we don't know how to go back down, right? Then we don't know how to do a mole to mole conversion. So just make sure you're really understanding what you're converting to and from. Don't try to just memorize the pattern, right? Okay. Let's try this one. I'll go ahead and balance it for you so you don't have to do that. Okay. So how many grams of SNF4 can be formed from 12.8 grams of hydrofluoric acid? Right, whenever it asks for what's the mass, we should be going to grams there. Okay, this one specifically asks for grams, but we need to make sure we're understanding context right there. Okay, so we want to get rid of grams of hydrofluoric acid and go to what? Moles of what? HF. Okay, so moles gets the 1. The molar mass of hydrofluoric acid is 20. Right? Hydrogen is 1, fluorine is 19. Okay, so I'm done with grams. Now I need to go moles of HF to what? Good. moles of SnF4. Okay, and these values need to come from where?
From the
From our coefficients. Good. Okay, and the molar mass of tin fluoride is 118.7 plus 19 times 4. 194.7? Okay, so before you do math, I would really make sure that we crossed everything correctly, right? All of our units cancel the way they should. So we do 12.8 times our molar mass divided by 20 divided by 4. No. 31.15? Right, this was just our molar mass. 197.4 was molar mass. Remember, I don't know why people do this, but some people try to put their final answer right here. Right? Don't do that. I don't know where that came from. Don't. Just put it somewhere else. Not in your T-chart. Okay? Questions there? Gram to gram? Feeling okay? All right, so